Let's continue our discussion of surface area. So remember that we have now parameterized surfaces. So we have a parameter space here. And for every point in that parameter space, it gives me some point on the surface. And last time we went over how to find surface area. What are the formulas that would give me surface area? This is what we call the surface conversion factor, or the surface differential. We saw that the conversion factor we need to multiply by this time is the length of the cross product of the partial derivatives of the parameterization. So the derivatives of the paths, what we call grid curves to the surface. And that is because the length of a cross product is in fact the area of a parallelogram spanned by those two vectors. So we had a formula for that if we have a parameterization in some domain, then to find the area of the surface, we have to do the integral in area with the conversion factor given by that cross product. We applied that to the particular case where you have a graph. So we have, for example, in this case, say z equals f of xy. And then what we have is that the parameter space may be, for example, well, something here. D. And then what we're doing is take that parameter space here and then just look at the graph above that parameter space, and we're trying to find the surface of that graph above that parameter space. And to do that, when the graph is just a function, then the formulas that we learned, these formulas in terms of cross products and so on, they actually simplify quite a bit. And what you have to do for the surface integral, you're doing the integral in area above d of this function, of the square root of 1 plus the square of the partial derivatives of your function f, okay? And as I said at the end of last time, that should remind you of the formula that we got for the length of a curve, of a curve that is a graph of a function. Okay, so that was the case when we had a function in x, y, and then we have a graph, and we were trying to find the length of the graph between a and b. That is the formula that you use to find that length, and that is the formula that you use to find the surface area. So let's do that for a particular surface area. This, what they're giving me is a paraboloid. That means that it looks like this. So this paraboloid opens up like this and like this. And they're asking me to cut it at z equals 9. Okay, so the surface that they're trying to compute is that of the paraboloid up to z equals 9. So let's see how to do that. This is the graph of a function. The domain, by the way, the domain is going to be the projection on the xy plane of this object. So to find the projection, since this is opening up, the largest projection we can get is when z equals 9, and the projection will be this, x squared plus y squared equals 9, which is the cross-section that I get as z equals 9, and this is a circle of radius 3, okay? So the domain of the parameterization is going to be x and y's with x squared plus y squared less or equal to 3. The parameter domain is all the possible values down there. And you can parameterize if you want to parameterize the surface the parameterization of the surface would be as u, v, and then f of u and v. So u squared plus v squared, where u squared and v squared are in that domain. So they are within, this is radius 3, so this is supposed to be a 9, and this is supposed to be a 9. Okay? So that would be a parameterization, but we are seeing the graph of a function, so I can just use the formula for the graph of the function. So again, the formula in surface is going to be the integral over d of the square root of 1 plus the partial with respect to x squared, partial with respect to y squared of the function dA. So here the function that I'm looking at is x squared plus y squared. So I can compute the partials, that is 2x, and the partial with respect to y is 2y. So I can then integrate over that region. I can parameterize the region in Cartesian coordinates, but you can see that there is a better way, hopefully you see there's a better way to integrate this than using Cartesians. This is going to be the square root of 1 plus 2x squared, so 4x squared, plus 4y squared in area. Okay? What's a better way to do that than Cartesian? In polar coordinates, because this region is a circle, and you can see that there is, you can replace this as 1 plus 4 times x squared plus y squared, which in x squared plus y squared in polar is just r squared. So we can replace that nicely in polar. I want to emphasize that the third exam is going to be on new material that we haven't covered. So I think chapters 15 and 16, material that we have not covered since the second exam. But this material uses a lot of material from other chapters. Okay. So for example, here I'm going to do this integral. I am using polar coordinates. So that is from like the first exam. All right. So even though this exam is not cumulative in the sense that we're going to just do integrals, parameterizations and things like that, surfaces in the exam, some of the things we use are from previous exams. So I would definitely suggest that you start also looking through some of these things, and that, for example, that you use this exercise to just remind yourself how to do polar coordinate integrals. Okay, so I'm going to then integrate, I'm doing the integral d of 1 plus 4 x squared plus y squared in area. I'm going to use polar coordinates. Remember, in polar, the change of variables is that x is r cosine theta, y is r sine theta, and that's it, because we're in 2D. And it's not cylindrical, so, and then the differential of area is r dr d theta. Here we are doing the integral of the entire revolution of this surface, so it's below the entire circle. So theta, it is going from 0 to 2 pi, and the radius is going from 0 to 3, is the filled-in circle, in the parameter space is the filled-in circle, so the radius goes up to 3. So that tells me that this integral simplifies to be from 0 to 2 pi, integral from 0 to 2, integral for 1 plus 4, and x squared plus y squared is r squared, so r squared, times r dr d theta. And that r saves me here because that r is almost the derivative of the inside, so I'm going to be able to do u substitution to do this integral. Any questions on setting up this this integral? Yes. Good point. Thank you. Yep. We said that the radius was going up to 3. Any other questions about the this change of coordinates? Okay, so now we can just do the integral. By the way, notice that this integral has no theta inside the integral. So this is the product of the integral in theta times the integral. I'm going to put the r in front. Whoops. Is the integral with respect to theta times the integral with respect to r. The integral with respect to theta, this is just the integral of 1 of an interval of length 2 pi. That's the length of the interval, so this is 2 pi. So now I just have to do the integral of, from 0 to 3, of r, the square root of 1 plus 4r squared dr. And if I pick 1 plus 4r squared to be u for my substitution, du will be 8r dr, and that means that r dr, which is what appears there, is an eighth of du. And when and the change also changes when r is 0, u is already 1, and when r is 3, u will be 3 squared times 4, it's 37. So this is the integral from, let me keep track of that, 2 pi. 2 pi times the integral from 1 to 37 of the square root of u du times an eighth. Okay? And you can do that integral. That's the integral of u to the half, which is 2/3 u to the 3/2, and so on. So what I get at the end of the day is pi over 6, 37 to the 3/2 minus 1. Okay, so now we also talked about surfaces of revolution. Remember that a surface of revolution is something like this. We take a graph in x, so something like this, and then I rotate it about the x-axis, like so. Okay, that doesn't look great. It doesn't look much of a surface of revolution, but now we want to figure out what is the surface area of a surface of revolution. So you can set up. Remember that these would set up as say in u and v. What was this? So there was something like the x coordinate is the parameter, and then we had something like if the graph in f, if it was x in, I guess in z, for example, I set up here, and this function was f of x, then we've set this up as f of x cosine theta, f of x sine theta, just to know what are the coordinates in x and y as we go along. So this is a parameterization for, let me change the parameters to u and v's. So this would be for u, f of u, and cosine v, f of u, sine of v. So I can use the formula, now that I have a parameterization for surface of revolution, I can use the formulas in terms of the integral with the length of the cross product of the RU. I can take derivatives and so on, compute the cross product, compute the length, and that is going to be the integral factor, the conversion factor for that integral. And what you end up getting is this formula instead. So that to integrate the area of a surface of revolution, what I end up getting is an integral of this shape, which again, you see that there is no theta at all inside. So actually what you get is the integral from 0 to 2 pi of d theta, which is 2 pi, times this integral, which is, I think, you may have already seen in calculus 2. You already saw this formula. What is the surface of, what is the surface area, surface of revolution? And you can deduce that formula using the general theory that we have for any surface, parameterized surfaces. So let's do it again. Let's use now that formula to parameterize this graph. Okay? So how am I going to, I'm going to reinterpret my paraboloid. This is x, y, and z. And remember that it does look like this. But I want to reinterpret it as a surface of revolution. What is happening here is that I am rotating about the z-axis, and I'm rotating this function, for example, in here, from here to here. If you just take that one function and rotate it, then I get a surface of revolution. So I can interpret it as a surface of revolution in that way. So let me do that. I'm going to write it as in the x-z plane. What happens? That was y is 0. The graph that I get here is z equals x squared. But notice that I'm going to be rotating about the z-axis. In this formula that we had here, the rotation was happening about the x-axis to get this formula as is. So when we rotate about the z-axis, I want this function to be expressed in terms of, as a function of z instead of a function of x. Okay? So maybe it makes more sense to actually look at it as z. Here is x. Here is the function, which is the square root of z. And then I'm rotating about this axis. Okay? So with that in mind, by the way, I have to reach all the way z equals 9. Okay? And those are the bounds that appear in this formula for a to b. So the surface area is going to be the integral from 0 to 2 pi, the integral from 0 to 9. So this is going to be in z and in theta. And then the function itself, the square root of z, times the square root of 1 plus the derivative squared. So what is the function itself is x is the square root of z. So the derivative of that function is 1 over 2 the square root of z. So the square of that is 1 over 4z. So what I get inside is 1 plus 1 over 4z. Okay? I can combine this, these two square roots into one. This is the integral from 0 to pi, integral from 0 to 9 of the square root of z plus 1 over 4 dz d theta. Let me stop here. Do you have any questions of how I'm setting up this integral as a surface of revolution? Yes. Yes, yes, I could have rotated. I have to rotate about the z-axis, but I could have drawn this function in the yz plane and look at it there. But at the end of the day, is the values, it's exactly the same function when I rotate it in that way. And it would look like y equals the square root of z. And it's the square root of z that is going to be my f of z that is going to figure in the formula. So the integral at the end of the day is exactly the same.
Would it
Yeah, yeah, I see what you mean. If this was z equals x squared plus y, then it would not have symmetry. It would not have a symmetry about the z-axis, so it would not be a surface of revolution.
So you have to use the other vector.
Right, exactly. Yep. And we're going to do that in a second. I have some other examples. I think I have another one for some, I think. But in any case, yeah, so I am able to do this in two different ways because it is a surface of revolution. If it wasn't, then I would have to just use the other form in that I'm just using the fact that it's a function of x and y. Great. So now you see that this integral, though, is completely different from the one we got in the other method. So this is just interesting that I get a completely different integral. So I can finish the integral, though. So the area I said is the integral from 0 to 2 pi, integral from 0 to 9, the square root of z plus a fourth, dz d theta. Again, there is no thetas inside, so this is the product of two integrals in theta times the integral in z. And again, this is just 2 pi. So I get 2 pi times an integral in z. How do you integrate that function? The square root of z plus a fourth.
Can you do u substitution?
What substitution did you suggest?
Like z plus 1/4, and then the derivative would just be 1.
Exactly. So the inside is just a linear transformation of z. So z plus a fourth equals u. That will bring the inside of the square root. So you just look at square root of u, and then the transformation works. So if I pick this change, du is just dz. And in that change, by the way, when z is 0, u is a fourth. When z is 9, I get 37 over 4. Remember that the solution had some 37 showing up. Here's how 37 is showing up in this integral, is in this way. So with this change of variables, what I get is the integral from a fourth to 37 over 4 of u half du, which is, I had a 2 pi that I should not forget. And again, that is the same value that we had before. Pi over 6, 37 to the 3 halves minus 1. So that's the solution. And it's the same you got from the other method.